Anywhere in that acceleration space could be zero, so we can just say, hey, we're at zero now. We're not accelerating.
Yeah.
Anyone can just say...
And they will stay continuously at 9.8.
Yeah.
Right? And that might be a static point in acceleration space.
I think that's what makes acceleration space different, is that I don't think it is arbitrary. You feel acceleration, therefore it's not just a matter of opinion.
If there was just one particle, then we would not even feel acceleration. I feel that.
We talked about this before, but I think it's because you only feel it when there's a difference in acceleration.
Yeah.
If everything in your environment accelerates at the same time, at the same rate, you feel actually nothing. Right? Because like when a car accelerates, it's only the car accelerating. You're not accelerating. Yeah. The car makes you accelerate, and that's what you feel. Yeah. But if you and the car accelerate at the same rate, you feel nothing. You wouldn't even know you're accelerating.
Yeah.
Unless you look out the window.
So hello everyone and welcome to AD Podcast. Today once again we are together doing some brainstorming and thinking about different aspects of our universe, the space, the time and the origin itself. So today we are going to have a lot more fun than we have done in our previous videos, and we are expecting a lot of enlightenment from Mr. Geoffrey Giles Stone. Welcome.
Thank you for having me. It's been a pleasant week, and I'm sad I'm going to be going in like 3 days, but back to my normal life, which is pretty nice.
Nice, right? So introducing Geoffrey, he's the author of one of the masterpiece. I'd like to get a hold of that book. Yeah. So here it is, guys. So we are going to start our discussion with this book itself, the one that he has created. And let's begin, right?
Okay.
So where is the rainbow? Let's start with rainbow. It's a very interesting topic, right? There are a lot of people who are very much confused about what rainbow actually is. So what is rainbow?
Believe it or not, I haven't spent too much time thinking out all the details of exactly why the rainbow looks how it looks and all that stuff. But basically, it's the same reason as a prism. Because when you see a prism, the light comes in here, it gets refracted, it comes out, and then you see the red is a little bit more refracted, or is it less? Anyway, the purple is, because the refraction occurs differently for each wavelength, you get this spreading out, and then you see all the colors.
And just after rain, the droplets in the atmosphere are acting as prism and creating that beautiful scene, right?
Yeah, so each one's reflecting and then also refracting the light. And so you see the rainbow on the opposite side of the sun.
Yeah. The sun is always behind, right?
Yeah, and because the refraction happens at a certain angle, you could look at the sun, go 180 degrees, and then away from that, the angle is exactly or roughly 42 degrees.
Okay.
Because that's how much it refracts in water. And
what does rainbow have to do, has to do with your concept? We have been discussing about the selection theory of light, and you have presented it as an alternative to Einstein's relativity, right? It's a kind of a detailed understanding of why things are happening fundamentally. So, okay, before getting that, we'll talk in a very deep way about this. Before getting that, let's have clarity about what relativity is and what kind of problems it's been creating. Like, why do we need another theory? What does relativity explains?
So prior to the invention of quantum mechanics, there were some questions about light. First of all, how fast does it move? Okay, we kind of figured that one out. And then, what is it moving through? Is there an ether? That was the default assumption. We call it ether. It's whatever the medium is that light travels through. If it's a wave, it's got to be traveling through a medium. It certainly seems to be a wave.
Yeah.
So a deliberate experiment was set up, Michelson-Morley, to see how fast is Earth moving through the ether.
Yeah.
So we could sort of measure the ether, because there's just no way to detect it nor measure it, right? It's so important, and yet it's so mysterious.
Yeah.
So that experiment determined that as the Earth is rotating, it doesn't seem to the interferometer that we made doesn't seem to be moving relative to the ether, even though the Earth's rotating, and even though it's orbiting the sun, it's still not moving relative.
No effect at all.
Nothing. Yeah. So it's like whatever this ether is also rotating with the Earth and moving with the Earth around the sun, which is bizarre because, how can, if starlight's coming from millions of light years away, this ether is somehow attached to the Earth and attached to those distant stars? That doesn't make sense, right?
Getting to a conclusion of absence of ether was a kind of crisis in physics, because there was a time when from hundreds of years scientists were working on things like light based on the understanding of existence of ether, right? Even the Maxwell equation that we still follow a lot, it was actually based on the existence of ether originally. And we also had like a lot of very great scientists like Lorentz himself. They were very much inclined toward the existence of ether. So Michelson-Morley experiment in 1887 was a kind of a disaster to all the scientists, because they found out that there is no ether, there is no motion.
Yeah. And in addition to that, Einstein also noticed that Maxwell's equations do assume an absolute frame of reference, which everyone knows ever since Galileo and Newton. We've known, no, there is no absolute frame of reference, or at least we think that. So that's basically where Einstein's theory comes from, is he's taking Maxwell's equations and he's realizing there must be some, how do we add relativity to that? How do we make Maxwell's equations compatible with Galilean relativity? And that's how he came up with the light clock thought experiment and the rigid rod thought experiment.
We can call it in a way that there was a time when all the theories existed based on the existence of ether, and since there was no detection of ether, people were thinking of something. They wanted something that would explain the universe without the use of ether. And that's what Einstein did in 1905. And he came up with an idea that we could explain things like time dilation, things like length contraction, which were previously explained by scientists like Lorentz himself. And he came up with an idea that he explained both these things, like time dilation and length contraction, based on the absence of ether. He didn't consider the existence.
Is that really what you want to say, though, that he's explaining it? Because I thought he sort of came up with it. Like it came from the light clock thought experiment. It came from...
No. It was far before Einstein.
So they had experiments showing that there was time dilation before Einstein?
Yeah, there were different kind of relativity in that time. There was Galilean relativity, and when Lorentz came up with this idea that there might be the delay of time happening, and he even had the formula. Even the Einstein, when it comes to Einstein, when you talk about time dilation, when you talk about length contraction, you always have a gamma there, right? The Lorentz factor, which was before Einstein.
Right. Actually, there's somebody else like Voigt. You ever heard of Voigt? Voigt? Apparently, he was the first one to come up with the Lorentz equation.
Okay.
Yeah.
And that was happening. So he came up with a theory.
But it is strange to come up with an explanation for something you haven't observed yet.
Yeah.
Right?
Yeah. And coming up with the Einstein's relativity, people were excited. Yeah, they at least had something to solve the crisis. And that might be the main reason why there were so many people following Einstein's path, because we didn't have any other options. Even now, when you talk to someone and tell that there's some problem in Einstein's theory, there's some problem in relativity, then there's only one question, like, do you have anything better? And most of the time we have no, but not today, right?
Right.
Not today.
So I think I came up with something better.
Yeah.
And that's because I'm using quantum mechanics, which didn't exist in the time when Einstein published his 1905 papers.
Yeah.
Right?
And there's a problem, like now talking about quantum mechanics. Now we have quantum mechanics, like you said. Like then there were nothing like quantum mechanics. We just have a classical mechanics. We just had classical mechanics. Now we have quantum mechanics. And when we compare the foundations of quantum mechanics and relativity, that's completely different. There are things like superposition, there are things like entanglement, which relativity is not being able to keep up with. Right? Relativity can't explain gravity. We can't expect general relativity getting aligned with the concept of superposition, because once we consider superposition, we don't know where the curvature is happening. If a particle is existing here, 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 and there, then where is the curvature? That's the question. And there are things which made people, which made scientists, which made physicists from all around the globe question about relativity. And we were always stuck with the question, like, do you have anything better? And today we have something. You have come up with a theory which deals with super velocity, the super wave nature of light, and it would be great if we hear it from you.
So I'll begin at the very beginning. So Einstein took us on a path. He redefined speed, essentially, because we've had a few changes in our definition of speed. This is how I think. I didn't really think about it when I wrote the book, but this is how I think about it now. Originally, before Galileo and Newton, speed was just distance over time.
Yeah.
And that equation was very useful. You can get time from distance and speed. You can get speed, you can get distance, all those. It's a nice, neat equation. You can rearrange the letters and get what you want. So the thing that Galileo and Newton did was introduce the idea of a frame of reference, or the idea that all motion is relative. So if all motion is relative, that equation is only useful if we assume that we already know what the frame of reference is, and it doesn't change. We don't have multiple frames of reference, and it's not arbitrary. But because we can have multiple frames of reference, or at least we think that after Newton and Galileo, and it can change and it's arbitrary, we need to abandon this equation because it only has now a very limited use. So how do we change this concept? How do we change our concept of speed? Einstein said, well, speed, he kept the definition the same, essentially. He went backwards to say that speed is just something within your frame. It's a very subjective thing. So you're going at 30 kilometers in my frame, but at 10 kilometers in someone else's frame.
Yeah.
And they're both the real speed. I say that's not enough. That's true in a sense, like it's part of the truth. But the deeper truth is that speed is also a relationship between frames. So that's how we keep it relativistic.
Yeah.
Speed is a relationship between frames, and it's symmetrical. So if I'm going 100 kilometers in your frame, you're going at 100 kilometers per hour in my frame.
Yeah. So does this mean that we know that as per Einstein's relativity, if something is 1 kilometer to me, it might be 2 kilometers to someone else, right? It might be 0.5 kilometer to someone else. And if something is now for me, it can be then for someone else. There's nothing like simultaneity. There's nothing like the real length, right? Are you like diverting from this direction?
I keep time. I also changed the definition of time a little bit. Like I keep it more like how it was in Newtonian and Galilean. The concept of time is that it's absolute.
Okay, time is absolute.
It's relative in the sense that my now is different from the tomorrow me is now.
Yeah.
And the time in which, say, year 0 happened, that's arbitrary. We could have chosen any time for that, right? We could have chosen different number of hours in the day and all kinds of things. We could have done differently, but because my theory doesn't really contemplate time dilation, I think simultaneity can be a real concept. Like there is a such thing as two events very far apart happening at the same time.
Yeah.
No matter what frame of reference you're in.
And this is where you differ from Einstein. Yeah. How do you explain the time dilation that we have been calculating? Because we already have a lot of evidences when it comes to time dilation. Like we recently had an experiment, Haffield-Keating experiment, right? And in which 2 flights, commercial flights, were flown in 2 different directions, and then the times were compared with something on Earth, and the time dilation were calculated, and we had it correct based on Einstein's relativity. So how do you...
I checked the math on that, and the predictions, I can't figure out where they got their predictions from. It doesn't match Einstein's. I don't think they were testing special relativity. However, what they were measuring was acceleration. So they went all the way around the world. To do that, you have to accelerate. And so that acceleration is quite a lot. But it has a slight effect on the atomic clocks. So just as gravity affects, so more intense gravity, the force, like when you feel that force, it affects how the atomic clock works. It slows it down.
Okay.
So does acceleration. If I accelerate that atomic clock, it feels the force, it slows down. That's what I think happened.
So is it like you agree upon the gravitational time dilation and not the inertial time dilation?
I agree with the experimental results. I just interpret them differently. I think it's just a clock effect. I think that the gravitational time dilation is a clock effect.
That sounds...
It only applies to atomic clocks. It wouldn't apply to a pendulum clock. If you did it with pendulums, you wouldn't see any difference.
Yeah.
Even if you had super precise pendulum clocks.
Yeah. The gravity would have some effect on that, right?
It has an effect, but it's the opposite as what's predicted by special relativity. So it blows special relativity out of the water.
Okay. So you mean that the difference in time that has been that are being calculated are actually the difference occurring in the clock only?
Yeah.
Okay, that is a very interesting take, I would say. So let's move to the foundations of your concept. Like you are standing on the concept of velocity space. And I found velocity space very interesting, especially after I read your book, because we have been studying Newton's law. Like if something is at rest or in uniform motion, it will stay in its uniform motion until undisturbed, right? So it is very different from what we used to think in our ancient times. Because there was a time when we had an understanding that said that for something to move at a constant speed, Gorkha International Travels for the collaboration with AD Podcast. र हामी गर्व गर्छौं नेपालको सबैभन्दा उत्कृष्ट ट्राभल एजेन्सीसँग कोलाबोरेसन गर्नुमा। कुनै ट्रिप प्लान गर्दै हुनुहुन्छ भने गो फर इट। नेपाली मनका नेपाली पाइलाहरू Capital Shoes. Congratulations Capital Shoes for the collaboration with AD Podcast. For a long time, we need some constant push, right? That's what we thought, and eventually we came to know that no. If something is in motion, if we throw something in space, out in space, then it will continue moving at the same speed until undisturbed. And in velocity space, talking about velocity space, something moving in uniform motion is actually at rest in velocity space.
There you go. Yeah.
And something moving in uniform motion at different speed is at some distance from the other point, and the distance shows the relative velocity, right? That's what I think I've got, and it would be, I want you to elaborate more on this with some examples as well.
So the velocity space is a little bit more abstract. So you can be, if you're at rest in space, there's only one way to do that. But to be at rest in velocity space, there's tons of ways to do that. You can be in inertial motion at any speed and in any direction.
Any speed, right?
As long as you're in inertial motion, you are at rest in velocity space. So some examples. I put in my book like some images. So fun fact, the length of Earth's orbit in velocity space is 187 kilometers per second per year. That's an acceleration, right? Because if you cover a distance in velocity space, and Heffeli and Keating, they covered a distance. When they went around the Earth, they covered a distance in velocity space. That means you're accelerating. Anytime you start at one point, end up somewhere else, or you can end up at the same point, right? With Earth. Earth starts at one point, goes around, ends up the same point. It's like it hasn't moved. But they have. We've covered a huge distance in velocity space. That means we've been accelerating the whole time.
Okay. That is interesting. And now about the rainbow. How is rainbow related to your concept? So
the rainbow is an analogy.
Okay.
So I also use the shadow sometimes, or a reflection, right? So it's useful for many reasons, but it's not real. So if you think it's real, you'll get confused.
I used to think when I was a child, I used to think that there's a pipe and there's something like flowing from this end to that end. But now I think I'm a bit clearer. And today I'm going to get like enlightened about rainbow.
I'm sure cartoons have confused a lot of kids.
Yeah.
Right? And those Skittles commercials, they're notorious. Like, have you ever seen a Skittles commercial where you didn't have a three-dimensional rainbow? Like,
yeah, kind of a cylinder bent, right?
Not only can you touch it, you can taste it.
Oh, really?
Right? That's their slogan, taste the rainbow.
Taste the rainbow.
But yeah, really, a rainbow's just an image on the back of your retina, and it doesn't actually exist anywhere outside of that, unless you take a picture of it, and then it would exist on the picture, right? So that's my metaphor for the speed of light. So the speed of light is just like a rainbow. The speed of light is basically an illusion. It's a perspective that you have, that the only reason you think it has a constant velocity is because you have a specific location in velocity space, and that it actually does have what you see has a constant relationship to you in velocity space, just like the rainbow does. Because if you move, the rainbow moves also.
Yeah,
it has to stay with you, just like your shadow does too. It's another good analogy. If you run, your shadow keeps up with you.
Yeah,
you can't outrun it.
Yeah,
no matter what you do, you're not going to escape from it. That's because there's a dynamic happening. It's not that the shadow is preventing you from running faster. There's no speed limit.
So that is how you are relating the invariance of speed of light with respect to observers, right? Because in special relativity, it's a I call it very weird postulate, which tells that the speed of light is constant with respect to observer, and how simple it sounds. It is that weird if you try to think deeper about this. Like, if you shoot a photon toward me at speed like 3 lakh kilometers per second, and I'm trying to get it faster, I try to move toward it like at 2 lakh kilometers per second, then like intuitively what we think is I'm going to reach that photon at like 5 lakh kilometers per second speed, right? But that doesn't happen with photon, and that happens with all other waves, all other particles, but not with photons. And that is what you are trying to explain with using the analogy of rainbow.
There's a lot. I always try lots of different things because if one analogy doesn't work, we'll try another one.
Yeah.
But so with photons, let's imagine we discovered a new particle. Let's call it a stillon.
Still on. Okay.
The stillon never moves.
Never moves.
Like really, really never moves because no matter where you move, how fast you move, it always stays still in your frame. It's always still in all frames. Okay.
Still in all frames.
Completely still in all frames.
Yeah.
That would mean there's a special kind of speed that this stillon has. Every other speed varies depending on your frame of reference.
Oh.
But not this one. This one is special. And that's what Einstein does. He says, he doesn't say this, but he makes it so that there are two different types of speed. There's the normal speeds of everything. Then there's the speed of light, which is the same. So a normal speed would be variable, completely dependent on your frame of reference.
Yeah.
The speed of light is invariant.
Invariant.
Completely. It's not just that it's fast, it's as invariant. Which makes it almost like a separate kind of thing. Almost like you need a new word, not speed, something else. But there's more to it because it's not just that there's two discrete categories, variable speeds, invariable speeds. There's a continuum between them. So the idea is the faster you move, the less variable your speed is, according to Einstein. So if you move at the speed of light, now your speed is invariant.
Invariant. Okay. As we are approaching the speed of light, we are moving toward the invariancy kind of. Okay. Okay.
I think that doesn't make any sense, but that's sort of how people think about special relativity.
So how is it very different from your concept? Like you have explained light as a super wave, a kind of a superpower added to a wave, right? So how do you explain it?
So super wave is like, I use the idea of a wave is to a particle as a super wave is to a wave. So light is a super wave because it behaves like a wave, but it's a little bit stranger than a wave in many different ways. So it doesn't have a polarity by default. It's all polarities. And then when you measure it, it has polarity, not before that. It doesn't have a position or a direction until you measure it.
It doesn't have a direction.
And then it also doesn't have a speed until you measure it. But at least if you know what the speed of your where your apparatus is in velocity space or where the observer is, then you can predict, based on the light bubble of manifest light, you can predict where it will be, where the light will be that you see in velocity space.
Okay, so light, interpreting light as, or understanding light as a super wave and having a very different character of being observable at one speed to all of us, right? For me, the speed of light is c. Then for someone moving at any speed, the speed of light is still c. That is how it makes light different. And talking about relativity, the main problem when we discuss about relativity is it doesn't fit properly with quantum mechanics. Have you thought of finding any compliance of your theory with quantum mechanics, or have you found any link to it?
Well, what I'm trying to do is, so I've sort of tried to blow apart special relativity, and I'm doing the same thing with quantum mechanics.
Yeah?
I haven't come up with a simple theory to explain everything yet, but I have seen, I've taken very seriously the idea that there are deep problems in both.
In quantum mechanics as well.
In quantum mechanics, it's just the fact that we don't have a theory. Like people say, quantum mechanical theory, it's not, it's an equation. It's a Schrodinger equation. and we have to interpret this equation.
And there are a lot of interpretations, and something having a lot of interpretations means that someone still has to get it right.
It's funny even that we call it interpretations. I think that's almost like a PR move, because it's trying to say we're all in agreement here and we have a theory. If we called them theories, which is what they are, each interpretation is a theory, then it would show that we don't have a theory. We have many theories. We don't know which one's correct.
Yeah.
And all we have are mathematical formula that make probabilistic predictions that we have no explanation for.
Yeah. Do you believe in, it might be like out of the box, but out of the content or out of our flow, but do you like believe in free will?
Oh, I do. And
when in the perspective of quantum mechanics, how you understand quantum mechanics based on that?
I don't think most physicists and engineers believe in free will. I think a lot of the mathematical types...
Actually, there's a reason as well to not believe in free will, because what are we made up of? We are made of molecules made of atoms made of like proton, neutron, they're made of quark, and their evolution, how they evolve in time, is based on Schrodinger equation, right? Schrodinger equation is an equation that tells how particles evolve in time, how we evolve in time at like subatomic level, right? And we also know that going from one state to another, like in classical mechanics, if we have speed of a ball, the gravitational influence of Earth, and the resistance of air, if you have all the parameters like known, then we can easily calculate what is going to happen in future exactly, right? Yeah. Where it is going to land, and what is the force with which it is going to land on Earth, right? But in quantum mechanics, even if we have the initial conditions, even if we are like known with the initial conditions, we still can't make the exact prediction what is going to happen next. Yeah. And what is going to happen next is completely random, not like relying on any theories of that we know till date, right? It's completely random. So the thinking is, I would like to complete it. So the thinking is, if what we are made up of is evolving in a random way in time, then at what point are we deciding what is going to happen in future? It might be that even I talking to you is random, is due to those random evolving in time. So that kind of disrupts the concept of having free will. Don't you think so?
Well, there's a lot to talk about now.
Yeah.
I devote a lot of my next book to the discussion about free will. Sabine Hassenfelder.
Yeah.
I really appreciate her. She's a good physicist, makes good videos. She's a determinist. She doesn't believe in free will. So there's really only two philosophies that are prominent. One is hard determinism. Mm-hmm. The other is something called compatibilism. And I'm a compatibilist, which just means I think that you can have a deterministic universe, completely 100%. Forget quantum mechanics. Let's just say there was no quantum mechanics and everything is like Laplace's universe, completely deterministic. You can still have free will.
Yeah.
Because I'm going down into what do we mean by free will? How is this a useful concept? And I'm saying it's perfectly intact and useful in a world that's totally deterministic. It doesn't mean what some people take it to mean. So just because you can predict what someone's going to do doesn't mean they didn't make a choice. For example.
Okay. Yeah. You have a like different take on that. Okay, let's get back to the theory.
Also, what do we mean by randomness? When it comes to quantum entanglement?
Yeah. What do you mean by
randomness?
Randomness. Okay.
So when we're observing an EPR type experiment, and let's say the two variables are perfectly correlated. Okay. So it's the angle of the detectors is such that we get spin up, spin down, spin up, spin down, spin down, spin up. Okay. It's always predictable once you have one. Yeah. So if you look at what's happening at either detector, it looks totally random. I look at detector A, totally random. Detector B, totally random. compare them side by side,
Not random.
not completely predictable. If I see what happens on this detector, I know what's going to be in the other one. So is it really random? That's always a question we have to ask. Just because we don't know or we can't see a pattern doesn't mean it's really random.
It's just a question of scale.
It's a matter of like how can...
It might be a matter of scale. It might be correlated to something that we even don't know about today. And one more explanation to quantum entanglement may be that they might be somehow connected in higher dimensions, right? Have you heard any interpretations on this?
I don't know about dimensions, but I suspect, well, I'm pretty sure that the correlations are due to a third variable. So it's not...
There's a hidden variable?
Well, yeah, and we don't know what it is. So what happens at detector A doesn't cause what happens at detector B. And what happens at detector B does not directly cause what happens at detector A. Rather, there's a third variable that causes both of them. And that's why we see...
Is it like the EPR paradox, like Einstein, Podolsky, and Rosen came up with the left foot shoe and the left glove and right glove, and if we detect somewhere that we have a left hand glove, then the other must be the right one.
Right.
Is it that way?
Yeah.
Okay. The beauty of quantum mechanics is any interpretations have a lot of points that support that interpretation, right? And similarly, it has a lot of points that completely destroys it. Like just like you explained right now, in the way EPR paradox did. There is a question arises when we talk about the Bell's inequality. It completely collapses the EPR paradox, right? So we got to think about that as well, because it's always a loop in quantum mechanics. When you go for a Copenhagen interpretations, it has a lot of points that support Copenhagen interpretation. If you go for pilot wave theory, there are a lot. If you go for a hidden variable theory, there are different explanations, different pros and different cons, right?
Yeah. I think you need to have a hidden variable interpretation in order to think that there's communication between, say, particles.
Yeah.
Right? So like, oh, I've been detected. Okay, now you're supposed to be this. Okay, and then it sends some signal, and then it sounds very unrealistic. Can you imagine particles thinking and communicating? And
no.
I can't imagine it.
There must be a hidden variable. But before saying this, we should take a pause, because there are a lot of concepts that are against the existence of hidden variable as well. Okay, yeah. So you are trying to connect your theory with quantum mechanics in your coming book. We can expect that, right? Okay, very excited for that. Very excited for that. And we are having a very, very smooth and very interesting discussion. And we will take a short commercial break and we'll be back. See you. And thank you, National IVF Center, for the partnership with AD Podcast. Welcome back after the short break. Welcome back.
Welcome back.
We were talking about determinacy, right?
Yes. So I'll just explain why do I still believe in free will if we have a deterministic universe. So I think that because the idea of free will is kind of strawmanned a little bit. So I think for a useful concept, it has to be practical, and we have a very practical, useful concept of free will. And it's a relative concept. So free will is not absolute. Nobody has absolute free anything. Yeah. Nothing can be absolutely free.
No.
Everything can be relatively free. And there are degrees of freedom, and there are degrees of being constrained.
Yeah, the way we make decision in a very comfortable room is very different from when we are kept near a volcano, right?
Yeah.
Our free will is being influenced, right? We just, if we are left in a jungle, our free will is just after the food.
Yeah, and we know that when things are more free, they also become less predictable. So we're imagining a universe where everything is perfectly predictable, and we think, well, then everything is not free. But that's actually not quite it. So I say free will is relative. I also say there's three basic variables that we can use to sort of gauge how free someone is, right? One is the decision making happening in their brain, or is it outside of them? So if you imagine like a boat choosing which of two streams to float down. If it just kind of goes with the water and then the water chooses, then it's not making the choice. But if it has some little contraption in there that chooses which river, then it's making a choice. Even if that little contraption is also just a boat floating down a river. Like you could make a little model of a boat in a river, and it just randomly chooses one stream.
Yeah.
Then that makes the steering wheel turn on the boat and guides it to one way or the other. But what I'm saying is it's relatively free because it's making a choice inside. The choice mechanism is inside the boat. The second one is, what kind of environment are you in? Do your choices actually matter or not? So there's a degree of that in our lives, right? I call it convergence versus divergence.
Okay.
Divergence, convergence.
Convergence, divergence.
So if everything is causally converging in your environment, then everything you do doesn't matter. And if we were heading towards a black hole, we would be in that kind of scenario where nothing you do matters, because no matter what you do, you're going to end up in that black hole. Divergence means small things you do make a big difference. So that's the second variable. So if you have divergence, you have more free will.
More free will.
And then the third variable is goals. So if you have some goal that you're pursuing, you have free will. If there's no goal, then your choices are sort of random and meaningless.
Meaningless.
And then you're basically lose free will that way.
So this is how you explain the extent of free will that we have.
Yeah.
It's not like binary,
Right.
1 or 0. Okay, that's interesting. Life is very like having life on Earth, and we tiny people when compared to the cosmic scale, experiencing the cosmos, like getting eyes to experience, like stargaze, right? Making rockets to fly in the space. How special do you feel life is? Like, and I would like to compare this with the Fermi Paradox as well.
Okay. Yeah.
How special are we? What do you think?
Special compared to what? Life is a miraculous, amazing, fascinating, beautiful thing.
Beautiful thing.
There's always more to learn about it. It's kind of fun to learn, so it'd be kind of a bummer if we knew everything about it, right? Yeah. But I think that is our goal usually, right? To know everything.
Yeah.
I don't know. It's it's pretty special.
Pretty special. What about the Fermi Paradox? Because it somehow tells that if there were any aliens, if there were any intelligent life out there, then we would have already met. MET, not MET till now, but we would have met.
I guess it depends on how you define intelligent life, but I think there's probably life somewhere else. If I was going to bet on it, I'd say probably.
Because we can't underestimate the size of the universe, right?
It's so hard. There's so many variables that if you get one of them wrong, you can get it really, you can be way off. But it's almost like we have a choice between either there's no chance of life anywhere in the universe, or there's absolute certainty. And which one is it? What are the odds that it's absolute certainty? What are the odds? I don't know. Like it's just, it's one of those really, like we're lost in the dark trying to find to come up with a probability. We don't have a frequency. How do you come up with a probability? At least I could flip a coin 100 times and see, oh, it's about 48. Okay. Have a frequency. I have something to base it on. We've got really nothing to base it on because we only have one example of a planet with life on it.
Talking about the entropy, the way we explain the evolution of life on Earth, and we compare it with the entropy principle, that the universe is so big that there must be some point where life must exist because it's infinitely big, right? What if we are the only life? And the whole universe is just for us? Because recently we have been seeing some observations that shows that our position in this universe is special.
Mm-hmm. That would lean me towards more of a simulation theory kind of scenario, because why would you bother to put anything out there that we're not going to interact with? It's just a background,
It's a background.
Set like a movie set or
As
something.
we move toward it, then it's getting created, right?
Yeah,
It's like the games.
yeah.
That's it.
Or some kind of, well, maybe that's what lots of religions have discovered. Like I think I've told you about Alan Watts. He talks about how, Eastern religions tend to see reality more as like a show or a production, right? It's not really real. It's there for us.
Yeah.
And it depends on our mind. Right?
It is said that everything is Maya. Maya means illusion.
Mhm.
Everything around us is Maya. That's what Hindu religion tells.
Yeah.
And when we get to the atomic level and we see we are made out of space more than stuff, then that makes us think, yeah, maybe we are just Maya, right? And just the illusion.
It's a really famous saying, right? If a tree falls in a forest and there's no one around to hear it, does it make a sound?
Does it make a sound?
And the Western typical response would be, yeah, it does. It makes sound waves. More of an Eastern take on that would be, no, it doesn't make a sound.
Why does it even have to make sound, right?
Exactly. It doesn't need to. What's the point?
Talking about the evidences, let's get deeper to Earth-centric, geocentric universe, because we have recently the Planck mission had some observations, the WMAP mission, where they were like looking for the anisotropies in this universe, and they came across a structure in which galaxies are placed around us. So they found that Earth is at the center and the galaxies are forming kind of shell. We can't tell Earth because the observations were not that accurate, but somewhere in Milky Way galaxy is the center.
Yeah.
And the other galaxies are like existing like shell at some distance. There's a shell and there's a gap, again a shell, there's a gap, again a shell. Why are we at the center of that shell? That creates a very big question, right? Why we are at the center? And if we are at the center, then a lot of physics theories are going to get simplified. We don't have to like hide our face by giving some nonsense explanation of cosmic inflation, right? We have easy explanation if we consider ourselves or the Earth as the center of the universe.
So how I would answer that is, anytime you find that the observer is somehow special, based on what the observer is observing, there's two possibilities. One, you're in a simulation.
Yeah.
It's not real. Or two, you've made a false assumption somewhere, forgot to consider something that like I mentioned this with the mirror paradox, right? Like,
That's please continue. Yeah. The mirror
I talked
paradox.
about this before. Like, if you assume that you're looking at a two-dimensional image that's been flipped along two dimensions, then you have to explain how this mirror knows left, right, from up, down, and how it. There's a lot of things. It seems to be a very intelligent mirror, but it's not. It's just a dumb flat surface, right?
Yeah, that we created, right?
But that's because you forgot to consider the front and back, right? The depth dimension. So if there's one important false assumption you made, you can create this observer-centered looking model.
That is exactly what Lawrence Krauss he said after this observation. He told like either all the explanations that we have to our universe based on the Copernican principle, either all of them are wrong and we are the center of the universe, or we need to do some more surveys. That's what he told. But initially when WMAP came up with this data, then there were a lot of skeptical people. Most of them were skeptical and not like trying to incline to that data. But when Planck satellite gave the same result, that was the time it was it already created a big elephant in the room. And now we should either ignore the Copernican principle or this big elephant, right? And not just this, we have cosmic microwave background as a very, very prominent proof that potentially we might be the center of the universe or somewhat special when compared to other parts of the universe, because when we observe the CMB, the background, then we find that the whole CMB is divided by a plane. The temperature difference are very minor, but the differences are divided by a plane into two parts. The sphere is divided into two parts using a plane, and that plane is exactly aligned with the plane of ecliptic, the plane of the solar system, and that's like mind-blowing.
I was encouraged when I heard about that. I didn't hear about that until pretty recently. Because my theory predicts that you should see something similar, not exactly the same thing, but that the ecliptic plane is very special.
Yeah.
Because when it comes to what I call parallax in velocity space, it should be much stronger near the ecliptic plane and then much weaker at the poles. What I think this should do is, I mean, yeah, it could be that we have a special place, but why? Why are we seeing this pattern in the CMB? What does that mean? So what really the question that we have to ask is, what is the CMB?
Yeah.
I don't think we know.
Yeah.
I think we've been pretending to know.
We have a lot of guests around, but we actually don't know. And what happened before the arrival of CMB, right? And that is still a question, and we have a lot of explanations, but I am not satisfied with what we have till date. So, and not just that, we have many other observations like the rotation of the galaxies. They found the correlations between our position, the ecliptic plane, and the rotation of the galaxy.
Wow.
And those.
Whoa, hold on. What's the correlation? Because that could prove my theory correct.
Yeah. I think I should give you the paper. I need a laptop. We can discuss it.
Because it should be that when it's close, well, there should be a large effect on the rate at which the galaxies appear to rotate if they're close to the ecliptic plane. Because the time is changing. It's just it's almost like a time dilation effect.
The direction of rotation is itself different. Like when you imagine the galaxies all around you, then you'll imagine some randomness. One revolving in this direction, one this, one anti-clockwise, one clockwise. But when we observed that, then we found that there is a region in space which was moving in one particular direction, and the other region in the other side of the ecliptic plane moving in the opposite direction. And not just that, we have a lot of proofs.
It also depends actually on how the rotation is measured. If they're using redshift, then that would lead me to one conclusion. If you're actually seeing it move, like you're using the visual angle, where it is in space.
Maybe the redshift might be the way that we can know in which direction it's moving. We see the shift, the shift of the wavelength of light in the one edge of the galaxy and the other edge, and the difference is how we come to know that which direction it's moving, right?
There could be just something wrong with using redshift. I feel like that could be a big thing. And if we discover that we've been misinterpreting redshift, we've already changed our mind a few times about how to interpret redshift. But if we are basically making a huge mistake, I think that could be possible. Hopefully we'll discover that pretty soon.
Yeah. And talking more about the anisotropy that we have, the inhomogeneity, right? The non-homogeneity or inhomogeneity that we have been seeing around us with the galaxies. There are many. And you have not heard a lot about Hinduism, but since we are together, I have talked a lot about it. I consider Hinduism as a bulk of knowledge from a civilization that knew far better than that we know today. The time when we were not sure if Earth was spherical. There was places in India where they had figures of many astronomical events. They if I ask you what's your birthday, then you'll give a date, month, and you'll give a number, 19 1982 or something like that, right? For us, it's easy. 1982 from the year zero, right? But for someone who has come from another civilization and who is not familiar with the dates, how are they going to know what you are talking about? So to explain the dates to them is very easy if we talk about the astronomical phenomena that has been happening. So that is how in Hinduism the birth date of the avatars of God were explained by explaining the planetary positions. Like Earth was in this location, Venus was moving in this direction, moon was in this direction, and that is how they explained. So that any civilization in future, if they want to know the exact date and they have good knowledge of astrophysics, then they can make the calculations and know what year the thing happened, right? So when you find a civilization that smart, and have you seen Ellora temple?
No.
Have not seen? Do we have like a phone? I want to show him a picture. Yeah. This is the temple. See, this is a huge temple. It is in South India.
Okay.
It is in South India, and the whole temple is made out of one rock. And the surprising thing is, it's not. And we are looking for some. Yeah, this temple is made out of one stone. Okay, wow. And a temple made out of one stone is very common in India. And having a temple that is carved out of one stone is very common in India. What is special about this is, this temple was carved from top to bottom. Okay, one stone carved from top to bottom. And where I am trying to connect is a civilization that had this level of structural engineering, architecture, and the knowledge of astrophysics. And when you talk about philosophy, we have Bhagavad Gita and a lot of different teachings that are very, very significant even till this age, right? If that civilization is pointing that Earth is the center of the universe, and not just Earth, they are actually pointing toward a mountain called Mount Kailash, and it is clearly stated that Mount Kailash is the axis mundi of the universe. It's the axis of the universe. Not just Hinduism, in Buddhism, in Jainism, you'll find the same thing, that Mount Kailash is the center of the universe. So these kind of things make me question that there are a lot of discoveries that we discovered, and later we came to know that this was already written in Vedas. This was written in Rig Veda, this was written in Atharva Veda. But this time, like our team, the team of Ancient Theory of Everything, we want to take things seriously when it's written in the scripture.
Okay, so they don't say why they concluded that this mountain is the center of the universe?
The thing is, in Hinduism, most of the scriptures you find that most of the things are given metaphorically, so that it can be explained to someone, it can be explained to the next generation in the form of stories. Okay, the main scriptures of Hinduism are like Puranas. They come out of Veda. Veda are the four major scriptures, and Puranas are like interpretations of Vedas in the form of story. And talking about Mount Kailasha or Earth being holding a special position, they have mentioned it a lot of times, but the story has been explained in a very metaphorical way. There is a city called City of Sambala under that Mount Kailasha, and Mount Kailasha is also known as the Swastika temple, Swastika mountain, and swastika indicates the four directions. You see the four limb in swastika, and it's same with the Nazi sign as well. The four limbs indicates to the four directions, or we can also say the four dimensions. So moving to the science, okay, I was trying to relate how the ancient civilizations are also pointing toward we being special in this universe, right? And now we have some scientific evidence as well when we talk about the quantized concentric distribution of galaxies, the anisotropies in CMB. These are all indicating toward we being special in this universe, and that is what we have held properly in ancient theory of everything. We explain time dilation, we explain length contraction, we are explaining the Schrodinger equation, derivation of Schrodinger equation, and many other things based on this one single concept. And that is, we are living in a three-dimensional universe, which is a cross-section, which is just a cross-section of a four-dimensional universe. It means if we see this three-dimensional mic, it's actually a shadow to a four-dimensional entity.
Mm-hmm.
And that is what relativity tells, right? But
Yes.
in relativity, it is told that the fourth dimension is time.
Right.
And we say that fourth dimension is space, and time is the effect of the motion in fourth dimension. Time is actually the consequence. The evolution is actually the consequence. And that is how we have explained time dilation using...
I think that's actually also what special relativity says. Because the time that we see isn't really time.
Yeah.
It's something deeper in space-time that causes what we see as time. But that's, we're only looking at it time from a certain perspective, according to special relativity.
The difference is, in ancient theory of everything, everything is absolute. As I told you, if something is 1 kilometer long, then it is 1 kilometer long for all perspectives,
So
all observers.
So there's no length contraction in ancient theory of everything.
We are going to talk about length contraction. That is due to the miscommunication. Length contraction actually happens due to the miscommunication between something that is in motion and the one who is actually calculating that motion.
In a thought experiment.
In a thought experiment, yeah. Okay, to get into ancient theory of everything, we start with the experiment that was done in 1887, the Michelson-Morley experiment.
Right.
Till then, we thought of space to be absolute, right? Things were considered based on the existence of ether. And when this experiment was done, we came to a conclusion, it actually had two conclusions. One, there is no ether. Two, there is ether, but it's stationary with respect to Earth. Those were the two conclusions. But in those times, we had no any evidence that showed that Earth can be special to this universe. And we can have something like ether, which is stationary with respect to Earth. So this conclusion was avoided. This conclusion was completely ignored. And we went for the second conclusion, that is, there is no ether. And Einstein came up with a theory which had no ether, and that's what we have been following in last century, right? Like more than 105 and 110 years.
So I guess the big thing about special or not special, first of all, it's a binary category, right?
Yeah.
Earth could be special in some ways and not in other ways.
Yeah.
But I think the reason people don't want to see it as special is because if you say Earth is special, you're implying that everything has been set up a certain way for Earth, right? The whole universe is set up, as opposed to things just randomly happening with no goal, no, predetermined goal, and just ending up a certain way, and you wouldn't expect them to end up in a way that's orderly and organized.
Exactly. This is how exactly people thought in those times. How can Earth be special? Like we have a sun which is far bigger than Earth, right? We have a galaxy that has more than trillions of sun, right? And now we know that there are trillions and trillions of galaxies, right?
And if you look at where Earth is in the galaxy, I mean, it's hard to see, but you can have people can draw a nice picture and make a model.
But now
it doesn't look special.
Yeah, but now after we have evidences like we discussed, the axis of evil, the CMB, and the position of the galaxies, now we have started questioning that are these evidences pointing toward Earth being special, right? And if Earth is considered special, once we consider Earth as special and having a medium or space, or we call field, anything, like we have started calling that vacuum is not empty, right? There was a time when we used to tell that vacuum is actually empty and we can't have anything like ether in nothing, right? And now we came to know that vacuum is not actually empty. There are energy fluctuations going on, and we can call that we have something there. We can name it field, we can name it ether, or we can name it as space.
Semantics, yeah.
Yeah, just like Einstein did, he just called it space and he started curving out the spaces.
Mm-hmm.
And now, after knowing these lot of things, we should also rethink toward the first conclusion that we had in Michelson-Morley experiment, right? The conclusion that Earth might be holding a special position. And as soon as we take Earth holding a special position, then things we can easily explain things to be absolute.
Well, yeah, once you have that as the foundation of your theory, then lots of things follow from that.
Yeah, lots of things follow. Because most of all the evidences that we have for time dilation, all the evidences that we have for like length contraction, all the observations were made taking Earth as their inertial frame of reference, right? And what relativity tells is law of physics remains same for all frame of reference, but we have not tested any physics laws in any frame of reference other than Earth's frame of reference, right? And by conducting experiment in one frame of reference and trying to apply that result to the whole universe in general, I don't think it's a right way to move.
I agree. It's like it's just a hasty assumption that was made and people followed it. Really should be tested, and it can be easily tested.
It can be easily tested. And to prove that Earth is not special or Earth is special, we have a very simple experiment designed, right? We can take an interferometer just like Michelson and Morley did, and we can take it to any non-geosynchronous satellite or any other planet or in the moon that is moving, that is in motion with respect to Earth, right? That has some motion with respect to Earth. And that will be a point when we will reach to a conclusion that A was correct or B was correct in the Michelson-Morley experiment.
Yeah, I think it should be done, and probably could be done very cheaply.
Yeah.
Does anyone know how to make the same kind of interferometer that Michelson and Morley made?
They probably should know because it's already like more than 35 years, right?
So everything should be easier, cheaper, more accurate.
Yeah.
Because we have better technology and more knowledge, so should be able to. I mean, we've learned a lot in 130 or 40 years, or yeah.
So there are a lot of questions to answer. There are a lot of mystery to solve. There are a lot of things that we need to like bring back together. Mm-hmm. And you are in a direction moving to find the why for special relativity, find the why behind the invariance of speed of light, and try to fill the loop of relativity. And we on the other side, we are working on finding the absolute answer to everything. Do we have an absolute frame of reference? Is relativity enough? Do we need a completely different theory to comply properly with quantum mechanics, or we should just like throw away both of these theories and start from zero?
Not zero, but Galileo and Newton. I really think they had given us a really good foundation. So let's go back to Galileo and Newton, and then rethink everything.
Rethink everything. We will be having a lot of discussions in the future as well, and we had some questions from our viewers, and I'd like to select one from Asim Bishta. He asks to you, how big is the universe? And this might be the last question of the podcast, so I want it very interesting.
Okay, well, I don't know. But, the usual question is, the big question is, well, we know kind of how big the visible universe is, but I don't think that's the question. The question is, how big is the universe?
Yeah, how big is the universe?
So we definitely don't know. We only know, who knows how much bigger it could be than what we can see. Another question would be, is it finite or infinite? That's a binary question, but I don't even know how to answer that, because what does it mean for anything to be infinite?
Yeah.
I thought about that a lot, and I think
What beyond that, right?
I try to think of concepts as practical, right? I don't want to get too abstract. So I think, what is a practical example of something that's infinite? You go to a restaurant, maybe, I don't know if you have any around here, but they'll serve you a bottomless cup of coffee. Okay, so that's infinite coffee, as much as you can drink. Free refills. Now, obviously, there are limits. The only reason they can offer you that is because, you can't drink coffee that fast. You can't stay forever. You only have so much space in your stomach and everything, right?
There's just 100 years in your hand, right?
Exactly. There's all these limits, and some of them are more important than others, but that's what allows you to have infinite coffee. Another thing I could say is that infinity is a number that I can't count to. Now, Gregor Cantor says there are countable infinities and uncountable infinities.
And it is also said that some infinities are bigger than other infinities.
Yes.
Do you agree with this?
I don't agree with that.
Even me.
But because I'm trying to stay practical, right? I don't buy into all of his concepts as constructs, and even set theory to an extent. But so what's a practical thing? I can't count to infinity. I don't think, even though if it's countable in some abstract hypothetical sense, I really can't count to infinity.
If it's countable, then it's not infinite, right?
I'd say that.
Yeah.
Right. So I can count 1, 2, 3. I'll never get to infinity. But what if I had infinite time and I could live forever? Well, then would I be able to count to infinity? Yes. So then the infinity goes away. There's no infinity anymore. It's only when it's beyond some threshold that when I'm limited, I say infinity is a product of limitations. So when you remove all the limitations one by one until you have no limitations, infinity disappears as well. So if I'm going to ask, like, how big is the universe, or is it infinite? It would be better to ask a practical question like, how far can you see, or how far can you travel? And you have to specify the conditions. If you could live 1,000 years, or if you could live 1,000,000 years, how far could you travel? And then if you traveled that far, how far would you be able to see? And how big would that total area be? I could go this way, I could go that way, I could go this way. Right? It's a practical question. But infinite is just,
Are we going to get back to the same spot if we keep traveling?
That's it. Right. That is a real practical question. Right? It's a question of, like, if I did this, what would happen? And then the question is, do you consider that infinite? That could be considered infinite. It's like saying...
Yeah, if something is cyclic, is it infinite?
Yeah. Is the Earth infinite? Because I can always move a little further to the west.
Yeah.
Right? I can always walk a few steps north, or I guess not once.
Not north. Not with the north.
Yeah. Sure, I can always go a little further east. And that's what I've been doing so far. I've already gone halfway around the world.
Yeah.
I'm going to go the other further east.
Yeah.
But yeah, you can always go a little further as long as you stay alive, and etc. Right? But that's not what people think of if they say is the Earth infinite. They were thinking like maybe infinite volume or infinite surface area or something like that, which I don't think they can really exist. But again, we're getting too abstract. I like to keep it practical.
Okay. So the universe, how big is the universe is the question, and the answer is, I don't know. After all these explanations. So it was an amazing discussion with Geoffrey, and we are looking forward for some more, and till he is in Nepal, and after that we will continue with our online podcast, and inshallah I'll be in Canada very soon, and we will have some podcast there as well. And in AD podcast we try to bring to you some new concepts that might spark some ideas in your mind, and you come up with some bigger concepts, and that is our goal. And we want to wake you up, we want to enlighten you with the facts, enlighten you with the logic, and enlighten you with physics. So this is AD podcast. Arif Ali signing off, and thank you, Geoffrey.
Please
take care.
Say something to subscribe.
Okay, to all our crew members and to the viewers, few words from Geoffrey.
Don't forget to subscribe to the channel.
Yeah.
Buy my book. Buy Arif's book.
Yeah.
And yeah, there are links below with more information.
Since you have watched this video till this point, we have a giveaway for you, like we usually do, and the giveaway is 1 Newton to now and a book, But Where is the Rainbow? And for this, you've got to comment down below, we love Geoffrey. So love you all, guys. पानी परिरहेको गरम गुरुङ रातैभरि मलाई के को चिन्ता म त थिएँ तिमीसँग गुड भाइब्स अनि मग मग स्मेल पनि फिल भइरहेको थियो मलाई मायाको तरङ्ग